Hello everybody, my name is Iman Esadi and today we're going to cover chapter 3 of organic chemistry. Here we will be talking about acid-base reactions and equilibrium. We're going to start off by defining some terminology like what a Bronsted-Lowry acid and base is, what a conjugate acid and base is, what pKa values are, and what a reaction mechanism is. And then from that, we're going to cover some fundamental concepts that are going to help us predict and compare relative acidity. And these are the pKa values and the OREO method. And finally, we're going to learn how to use either pKa values or the OREO method to determine the equilibrium of a reaction, the equilibration of a reaction. Where does the equilibrium lie? Are the reactants or are the products favored? Now, before we start with defining some terminology, I just want to make a few quick notes for you to keep in mind. These points are going to reappear in our discussion later, but I'm mentioning them now just because I think will be beneficial for you to keep this in the back of your head as we go through our discussion. Really quickly, whenever you see HA written, this is referring to a protonated acid. And if you see A minus, this is referring to a deprotonated acid. All right, and so here are the 3 quick points. 1, if your deprotonated acid is stable, all right, then the protonated acid, the protonated version of your acid is going to be a strong acid. Now, if your deprotonated acid is very unstable, then your protonated acid is going to be a weak acid. And the equilibrium of an acid-base reaction is always going to favor the more stabilized negative charge. So keep these 3 points in the back of your head. We're going to come back to this later. Now we're going to start by covering some definitions. All right, we're going to start off with what a Bronsted-Lowry acid is and what a Bronsted-Lowry base is. An acid is going to be our proton donor. It's going to give up a hydrogen, and it's therefore going to increase the concentration of hydrogen ions in the solution. Conversely, a Bronsted base is going to be a proton acceptor. All right, and so we want to keep that in the back of our head. Whenever you see a molecule with a hydrogen, all right, and in the product, it has lost that hydrogen, that is going to be acting as your acid. All right, and whatever molecule you see in your reactants and then in your products has gained a hydrogen, then this will be acting as your base. Water is interesting because it can act as an acid or base. Now, a conjugate acid and base, we want to cover what those are. Now, the products of a proton transfer reaction are going to be called your conjugate acid and conjugate base. Your conjugate base is what remains of the acid after deprotonation. After your acid loses a hydrogen, it donates a hydrogen, all right? What remains is called a conjugate base. Your conjugate acid is what is produced after protonation. So here you have your acid, all right, and here you have your base. Now, after the reaction has proceeded, your acid has lost a hydrogen, all right. What remains is called your conjugate base, all right, and here's your base right here, all right. It's been protonated, all right, and what it's called after protonation is a conjugate acid. Now, we can observe acid-base and conjugate base best through a reaction mechanism. All right. All reactions are accomplished via the flow of electron density, so the motion of electrons. And this flow of electron density is illustrated through curved arrows. The arrows are going to show the reaction mechanism to pretty much show you how the reaction occurs in terms of the motion of electrons. All right. Most bases you will see in this course are gonna have a negative charge, so they'll be easy to remember and to identify. Remember, water is gonna act as both, but clearly here, this is clearly gonna be an acid because it's gonna donate that hydrogen. And so in this reaction, your water is actually going to be a base. Excuse me. And we're going to illustrate this reaction mechanism since we know this is our acid and we know that this is our base, and our base is going to gain a hydrogen. The reaction mechanism is that this water is going to take the hydrogen from this molecule, all right, and the hydrogen is going to break off and dump its electrons to the bromine, and that's why you get this bromine with a negative charge. It has an extra lone pair, all right. The acid has been deprotonated, and it's now a conjugate base, whereas your base has gained a hydrogen. Look at that. It's now referred to as a conjugate acid. Now, the last term we want to define is pKa values. The reaction is said to have reached equilibrium when there is no longer an observable change in the concentration of reactants and products. All right, so it's reached equilibrium when the concentration of reactants and products are equal. There is no more change. So we want to describe this position of equilibrium using this term called KEQ, our equilibrium value. All right, and this is going to be defined as concentration of products over concentration of reactants. All right, so if we have here our traditional acid-base reaction, where this is our acid, this is a base, this is a conjugate base, and this is a conjugate acid. All right, we're going to quickly write the equilibrium constant for this KEQ, and we're going to put the concentration of products over the concentration of reactants. Now, when water is the solvent, the concentration is going to be fairly constant, and we can remove or move this water term over here. So if we move our water term here with the KEQ term, all right, this gives us a new term called our Ka term. All right, and it's pretty much still going to be your concentration of products over your concentration of reactants, just minus our solvent term, this water. All right, now if we take this Ka value and we do the negative log of Ka, what we get is this pKa value. Now, the term Ka alone defines acidity, but it usually has a really large range and it gives large numbers. So we simply take the log of it to keep it within a concise and smaller range. So that's why we take the negative log value of Ka. And what we get is this new term called pKa that helps us define acidity within a smaller range. Now, what we want to do is look at Ka values for some of the functional groups we discussed last chapter. All right, this is a pKa table that you can find in the David Klein textbook, and it's really good if you become familiar with the associated pKa values for most of these functional groups. Now, some important things to keep in mind. The stronger the acid, the weaker the base. There is this inverse relationship between the strength of an acid and a base. The stronger the acid, the weaker the base. All right. Now, how can you tell if an acid is strong? An acid is strong when it has a low pKa value. For example, the top here, this sulfuric acid, for example, it has a -9 pKa value, as compared to here we have an alkane, it has a pKa of 50, much greater than -9. Which one is a stronger acid? The sulfuric acid, the one with the lower pKa value. Now, this is a strong acid. The sulfuric acid is a strong acid. If we deprotonate it, we take away that hydrogen, all right, its conjugate is a weak base. All right, remember that inverse relationship between strong acid and strong base. When you look at the base, when you look at the acid and you say that it's a strong acid, all right, when you deprotonate it, when that hydrogen is lost, all right, its conjugate base is weak. It's a weak base. Awesome. Now let's go through some of these really quickly, right? This is an alkane, right? Just your normal hydrocarbon single bond. It has a pKa value of 50. All right, your carbon double bonds, your alkenes, have a pKa value of 44. All right, your amines has a pKa value of 38. Your alkynes, right, your triple bonds have a pKa value of 25. All right, here you see a ketone. All right, a ketone, but where this group has a hydrogen. All right, your alpha ketones. All right, they have a pKa value of 19.2. Here you have an alcohol group. All right, but you have an alcohol group here as well, and also you have an alcohol group here and here. All right, the difference between these two is the branches off, are the branches that are near this alcohol group. So more branches, higher pKa, less branches, then the less branches, the lower the pKa. Here you have water. All right, here you have phenyl. All right, with a pKa of 9.9. All right, here you have anhydride. This is anhydride. All right, has a pKa value of 9. This is your carboxylic acid with a pKa of about 5. All right, here you have your hydronium ion. It has a pKa of -2 about. Here you have alkyl halides. All right, about -7. All right, and then here you have your sulfuric acid. All right, with a pKa value of -9. It is the most acidic on this list. So make sure that you become quite acquainted with the pKa values of your functional groups. And the cool thing is you can compare two acids and determine which is more acidic based off of pKa values. Now, another way to do this, if you don't know or you don't remember your pKa values, is based off of comparing the conjugate bases of the acids. And this method is called OREO. So you can compare acids without use of pKa values by looking at the conjugate base of each acid. All right, and this is important. It gives you another way besides pKa to determine where the equilibrium lies in a reaction. Now, this method, OREO, each letter stands for something. A stands for atom. You ask yourself which atom bears the charge. All right, R stands for resonance, and I stands for induction, and O stands for orbitals. So, in the process of determining, all right, between two acids, which one is more acidic, and you don't remember the pKa values, what you can do is you can deprotonate each acid and then ask yourself these 4 questions to help you determine which is a more stable base. If you know which one is a more stable base, which deprotonated acid is stable, then you can tell which acid, when protonated, is a strong acid or a weak acid. And of course, we're going to do a few examples of this. Always remember that with OREO, there are exceptions to this rule, right? You first start off with atom and which atom bears the charge. If you can't answer this question because they're both the same, then you move on to the next, and the next, right? Following that hierarchy. But sometimes there are exceptions where OREO doesn't help you in that order, and that's why I always say knowing your pKa values is a better way of determining of comparing relative acidity, but it's good to know both. Now, to use this method, we're going to take the two acids or molecules that we're comparing, and then we're going to deprotonate both. All right, we're going to deprotonate both. And then we're going to go through each letter of OREO, starting at A, to determine which conjugate base is more stable. All right, sometimes you don't have to go through all of OREO. The more stable conjugate base is going to be your stronger acid when protonated. Okay, I just had to repeat that. That's a very important point. All right, so now let's do a couple of examples. All right, we're starting off with these two examples. We want to compare this molecule and this molecule. Which one is more acidic? Which one is a stronger acid? All right, stronger acid. Which one is a stronger acid? We don't remember the pKa values for either of these. Our first step is to go ahead and deprotonate both of these. All right, and we're going to deprotonate them. All right, so this carbon's going to lose a hydrogen. All right, the hydrogen's going to leave and it's going to dump its electron. So we have a negative charge here at the carbon. All right, and if this hydrogen leaves, it's going to dump its electrons on the oxygen, and now the oxygen's going to have a negative charge. So we've deprotonated both of these molecules. Now we're going to go through OREO to determine which one is a more stable conjugate base. All right, starting off with A. Which atom here bears the negative charge? In this first one, the carbon atom bears the negative charge. For this molecule, the oxygen bears the negative charge. All right, now which atom can deal with the negativity better? In other words, is the carbon or the oxygen more electronegative? The answer is obviously oxygen. Oxygen is more electronegative. What this means is it's going to deal with the negative charge better, and that makes it more stable. So this molecule is the more stable conjugate base. Now, if it's the more stable conjugate base, that means it's going to be the stronger acid. So that's a relationship you have to learn. The more stable a conjugate base is, when you protonate it again, it's going to form the stronger acid. So we go back to our original question. All right, which one of these two is the stronger acid? This one, because when it is deprotonated, it is the more stable conjugate base. All right, so that's how we're going to use OREO to help us determine which between two molecules, forgetting our pKa values, which one is the stronger acid. All right, let's do another example where we make it out to a further letter in OREO. All right, let's look at these two molecules here. Which one is a stronger acid? All right, we don't remember our pKa value, so our first step is we're going to deprotonate both of them. So we're going to deprotonate this so the hydrogen leaves its electrons with the oxygen and goes away. This oxygen has a negative charge now. We're going to deprotonate this as well. Same thing, hydrogen leaves, dumps its electrons. This oxygen is going to have a negative charge. All right, we're going to go through OREO. First letter, which atom has the negative charge? In both of them, the oxygen bears the negative charge. So it's the same. That question's not going to help us determine which one is a more stable conjugate base. So we move on to our next letter, R, resonance. Do the molecules participate in resonance? All right, for this question, well, no, there's no resonance. It's just a negative charge. It's not near a double bond. It's not near anything else. So there's no resonance for this. But if we look at this molecule, all right, if we look at this molecule, look here, we have a double bond, and in the allylic position right here, all right, there's a negative charge. There's a lone pair. This is an allylic lone pair. This is one of our patterns for resonance. So there is, in fact, this molecule participates in resonance. These electrons are delocalized and are going to be moving around here, participating in resonance. All right, so this molecule has resonance. Now, it has resonance and the other molecule doesn't. So this makes this molecule more stable conjugate base. And if this molecule is the more stable conjugate base, it's going to be the stronger acid. So we go back to our original question. Which one of these two is the stronger acid? It's going to be this guy right here. Awesome. Now let's look at another example where we have to go further out into our letter scheme to help answer the question of which is more stable conjugate base. All right, we're comparing these two molecules. Which is a stronger acid? We don't know because we forgot our pKa values. So first up, we're going to deprotonate both of them. All right, if we deprotonate this first one, we get that negative charge at the oxygen. We deprotonate the second one, we also get the negative charge on the oxygen. Now, we're going to go through all letters. A, R, I, O. Okay, which atom bears the negative charge? In both of them, the oxygen has the negative charge. So that doesn't help. How about resonance? Does this participate in resonance? Yes, look, negative charge near double bond. So yes, there's resonance. And here, same thing. There's a negative charge near a double bond. So yes, there's resonance. And it's going to be happening pretty much equally here. Look at the same kind of region that the resonance is occurring, that the delocalization of electrons is going to be happening. So resonance isn't going to help us determine which one of these is a more stable conjugate base. We have to move to I. All right, I deals with induction. All right, induction means are there electronegative atoms present nearby to withdraw some of the electron density? All right, if we look to the side here, there are no electronegative atoms. There's just carbon here. But if we look at this other molecule, it has 3 chlorines, which are very electronegative. It has electronegative atoms present. What that means is that those chlorines are going to withdraw some of the electron density. It's going to withdraw some of the electron density near those chlorine atoms. And that's going to make this molecule as a whole more stable. So this is the more stable conjugate base, which means it's also the stronger acid when it is protonated. All right, it's going to be the stronger acid. So we go back to our original question. This is going to be the stronger acid. All right, let's do one more example where we have to make it to orbitals in order to answer the question. All right, we're going to look at this molecule right here. We're asking, is this region or is this region more acidic? So we're going to deprotonate both of these regions. All right, when we deprotonate the double bond, we get a negative charge on the double bond. When we deprotonate the triple bond, we get a negative charge on the triple bond. All right, so here we're comparing okay, so we're going to go through OREO. All right, we're going to ask ourselves for atoms. All right, which atoms are bearing the negative charge? In both cases, it's a carbon atom, so that doesn't help us. Okay, in both cases, now we're going to go to resonance. Is there resonance that's going to happen in this area? No, that lone pair isn't not near another double bond. And this triple bond, this negative charge on the triple bond, is also not near anything that's going to participate in resonance. So no resonance for both. Okay, that doesn't help us. How about induction? Are there electronegative atoms nearby to withdraw electron density? Again, no in this case, and also no in this case. There's no electronegative atoms. There's just carbons around. So I doesn't help us either. Now we make it to orbitals. Okay, we're going to compare the kind of orbitals that the electrons are sitting in. All right, here, these electrons are going to be sitting in an sp2 orbital, right, because it's a double bond. And the electrons on the triple bond are going to be sitting in an sp orbital. Now, you need to remember this. Electrons in an sp orbital are going to be closer to the nucleus in comparison to sp2 and sp3. So what that means is electrons in sp orbital are going to be more stabilized by the nucleus. So that means this triple bond, this region right here, let's highlight it. All right, this triple bond, all right, is more stable conjugate base. That means it's going to be the stronger acid when it's protonated. Stronger acid. So when we ask which region is more acidic, it's going to be this triple bond right here. All right. So the whole point of OREO, of all these techniques, the whole point of OREO is to help you determine, after you've deprotonated a molecule, which conjugate base is more stable in comparison. All right. And then from that, determining which one is a more stable conjugate base is going to help you determine which molecule in its protonated version is the stronger acid. All right. The more stable conjugate base is the stronger acid when protonated. And ultimately, this is important in determining where the equilibrium in a reaction lies. And we're going to see this next. All right, we're going to see this next because we're going to see this next. So whenever you're given a acid-base reaction like this, all right, you're going to be asked to predict the position of equilibrium for a reaction like this. All right, does the equilibrium lie towards the products, or does the equilibrium lie towards the reactants? All right, and you have to figure that out. And the way you can figure that out to predict the position of equilibrium is using one of two techniques. You can use the pKa values to help you figure where the equilibrium lies, or you can use OREO to determine where the equilibrium lies. Okay, so we're going to go ahead. We're going to go ahead and do this problem. We're going to predict where the equilibrium lies for this reaction using both methods, okay? So our first step, whenever we get a reaction and we have to predict the equilibrium, is we're going to label our acid, our base, our conjugate acid, and our conjugate base. Now your base is going to be the one with the negative charge. So this is our base, making this our acid. All right. Now, whenever your base steals a proton from your acid, all right, it's going to be, the protonated version of your base is your conjugate acid. So this is going to be our conjugate acid. And then the deprotonated version of our acid is going to be the conjugate base. All right. Now we have everything labeled. We have our base, our acid, our conjugate acid, and our conjugate base labeled. All right, so we're going to learn how to predict the position of equilibrium first using pKa. All right, so here is the step-by-step method for doing the pKa, for using pKa values to predict the position of equilibrium. All right, your first step is to identify your acid and your conjugate acid. All right, your first step when you are using the pKa method is to identify your acid, all right, and your conjugate acid. So we've circled those here. Now, your second step in this method is to assign the pKa values for each. Now, your amine has a pKa value of 38, and this is just an alkane, just a hydrocarbon. It's going to have a pKa value of 50. All right, so we did the first step. We identified our acid and our conjugate acid, and we gave them pKa values. Now, you want to draw your arrow from, and this is miswritten, sorry. You want to draw your arrow from low pKa to high pKa. All right, so from low pKa starting, which is lower, 38 or 50. Obviously, 38 is your lower pKa. So you're going to draw your arrow from 38 to 50. And look at that. That arrow is going to tell us that the equilibrium is going to favor the products because we're going from reactants to products. All right, so that's how we use pKa to predict the position of equilibrium here. Our arrow is going to point towards our products. Therefore, equilibrium is going to lie in favor of the products for this reaction. Now, we can answer the same question using our OREO method. Now, using your OREO method, all right, if you forgot your pKa values, that's okay. You can do the OREO method. Here, your first step is to identify your base and your conjugate base. So we're going to circle our base and our conjugate base. Cool. Now, our second step is to determine which of these is more stable using OREO. Okay, so we're going to go through OREO here for both of these. Which atom possesses the negative charge? For the base, the negative charge is on a carbon. For your conjugate base, your negative charge is on a nitrogen. Well, which is more negative? Which is more electronegative, carbon or nitrogen? Well, nitrogen is more electronegative. And because it's more electronegative, that nitrogen is going to bear that negative charge better, making it more stable. All right, so your conjugate base is more stable than your base. And then your third step is you want to draw the arrow towards the more stable base. So since our conjugate base is more stable, we're going to draw our arrow towards the conjugate base. And so we're drawing our arrow towards the products. Our equilibrium lies towards the products. And look how, using either method, our pKa method or our OREO method, we reach the same answer in regards to predicting the position of equilibrium for this reaction. All right, I hope this made sense. Let me know if you have any questions at all, or if you would like to see more problems like this, go ahead and let me know in the comments below, or send me those questions to the email that's in the description box below. Happy studying, good luck, and have a great day.